Great. Good to see everyone. Thanks for being here, and thank you very much for the invitation to speak today. My name is Jim Owens, and I am the founder and CEO of Nautilus Defense. We're a small Rhode Island-based company that builds textile integrated systems, mostly for monitoring high-value assets in their environments for the defense and intelligence communities. But the same technologies that we use to build those environmental and asset monitoring systems translate also to a number of medical applications. So I'm not going to speak too much about those systems that we build today, or even the medical systems we built, but rather the fundamental enabling technologies that allow us to build garments for ambulatory multimodal biosensing and inconspicuous therapies, which, because we are a defense company, has an acronym that I'll continue to use. So I think it's important to start with, why are we talking about smart textiles, and why not just multimodal sensor systems more generally? And why are we really constraining ourselves to that material system, to that type of backplane? And really the answer is that for our clothes and for other applications, textiles are the optimal material. That's a very advanced technology designed to deliver very specific performance characteristics, and it's a very broad field. There's not just, we don't all wear the same type of textiles all the time. We don't use the same textiles for every application. So the science is very advanced. The manufacturing infrastructure associated with producing textiles at scale is very mature, which is why textiles are as ubiquitous as they are. But it really does all stem from their fundamental utility as a mechanical system. So beyond our clothes, that's also why we use textiles to land rovers on Mars and other things on Earth. It's why we build offshore mooring lines for tethering platforms to the ocean's floor with textiles, and why we build, scaffolds, stents, sutures, and other things with textiles for repairing our bodies. So the big properties that we care about with textiles, there's many more than what I'll speak to today, but we certainly care about how they feel, how they fall on our bodies, and that's called hand and drape. Very important. The fact that they can pack into very small volumes and then deploy and have a much larger effective surface area. This is very important for arrayed systems where you care about the aperture, and also for systems, obviously, where you care about their packing efficiency and how small you can stow them. There's a lot of things like this that we don't think about, but if you could never fold your clothes, they would take up a lot of space in your life. So very important. They have really best-in-class specific surface area, so very good surface area to mass ratio, which again is desirable for spanning large areas, making aperture arrayed systems, large aperture arrayed systems. And we can engineer their mechanical properties for strength and elongation to meet the needs of the system. And there's a huge amount of flexibility in the design space of textiles that we all take for granted, but it's really, if you start to pay attention to the ways in which textiles are made, it's all very deliberate, very intentional, and really tailored to the application. So the fundamental properties that enable these higher level textile properties are that the fibers, filaments, and yarns inside of textiles can move relative to each other. That inter-element mobility is really what supports them being perfect for dynamic systems that are designed to move. They are designed with multi-scale structural hierarchies. So at a given length scale, you're able to the extent that it's possible, maintain that inter-element mobility, but also have structural coherence at higher levels, higher length scales, and levels of that system. You can engineer their porosity for managing moisture and heat, which becomes particularly important as they become larger and cover more area, particularly on the human body. They can be engineered such that they can change shape without being damaged, right? They can dramatically change shape, return to their original shape, and last for a very long time doing that. And the coherence that I mentioned before, that structural coherence that forms a unified system from these disparate elements, is mostly maintained by friction, which is pretty powerful. There isn't, fundamentally, textiles are not adhered together. There's some other forces at play, but principally it's friction that keeps them together. So that's all really great for building dynamic systems that are, again, designed to move. But when you start to look at how that intersects the requirements and value of electronics, particularly, ever denser microelectronics, there's a mismatch there. There's just it's pretty fundamental in that silicon transistors, while amazing and a very important technology, they are rigid. Sure, you can thin down chips, you can make them a little flexible, but fundamentally, the technology is really designed to be rigid because of the materials that are used to build those parts. So those are really the two sides that you have to look at when you come at this and say, how do we build platform technologies that enable us to build a wide array of systems that have value in the medical space? So Nautilus approaches this by building basically composite systems. So it begins with the yarn. So again, that base unit where there's good inter-element mobility inside of it, and then we engineer it to include a combination of structural and functional materials. Typically, those functional materials are fine insulated conductor, using 46 gauge conductors. So they're about 40 microns in diameter, 38.3 microns in diameter. These are some of our bigger yarns, but they're designed in such a way that they strike a balance between the system level requirements for building in textile buses. So 1 and 2 dimensional routing between electronic devices inside of a textile. And they're compatible with subsequent textile manufacturing processes, including weaving, embroidery, braiding, knitting. It's really a very flexible technology in that way because inherently they are yarns. And the way we make these allows us to scale them down in a way that other approaches do not. There's fundamental limitations to how small the conductors can be that you integrate and how robust the yarn construction can be. So we do this composite braided construction, which is patented and patent pending, and it has quite a lot of utility in just the general construction of these systems. So we've done a number of studies to show that the conductors, while very fine and very limited strength themselves, in these constructions, they do not fail. They do not experience plastic deformation until the structural elements of these yarns fail. So that's a very valuable property when really the reliable and consistent manufacture of textiles relies on consistent tensions or tension throughout processing. So very important that we're able to provide that protection. So this is a picture of a finer yarn, a composite yarn with 25 micron diameter conductors and a hair from my head on the top for scale. So no measurement here, but just as a point of reference, we can really scale these down even smaller than what you see here. The limitation at this point is the structural materials that we can source that are strong enough and small enough. We have manufacturers that make us custom materials to enable this continuing scale down, which this is a measured yarn that also has 25 micron diameter conductors in it. It's about 160 microns wide and about 120 120 microns thick in the z-axis. And this is made with a filamentous yarn that just provides, because it's comprised of small filaments and how rod physics work, it is inherently much more flexible than the yarn that I showed you in the previous slide. So this is a really fundamental enabling technology in the construction of these types of systems. And at these scales, it allows us to do things that really can't be done with other materials, such as integrating ASICs directly, doing direct die attach on 2D textile networks. So this is a US quarter. This is a chiplet designed by Dr. Ben Calhoun's team at UVA. This measures 2.15 millimeters long by 0.6 millimeters wide by 0.3 millimeters high. And it has 12 pads on the bottom, and they are soldered directly to our embroidered conductive yarns here. These yarns are fully insulated, except where we ablate them with a laser local to the interconnect location. And this is an early device that has fairly simple routing capability, networking capabilities, but it's fundamentally the path forward. It's a great demonstrator and proof of concept of the types of integration that we can accomplish and how we can kind of marry the worlds of textiles and electronics in a way where we're not compromising the performance characteristics of either side of the equation. So this means we need to disaggregate and distribute compute capability and sensing capability as it makes sense. And that what that does is it minimizes the rigid surface area that we have to worry about in what is otherwise really a purely textile system. And we use those same yarns and embroidery techniques to also build electrode arrays. So shown here is a part of a larger system that has many more electrodes and is spread over a much larger area. But fundamentally, we have these insulated conductors, which are de-insulated, where we're interconnecting them using processes to silverize conductive yarns. They don't have to be silverized. They could be conductive via other materials or inherently conductive. But the technology really is flexible in the types of structures that we can build that are textile native. And we can make decisions about what should be made using traditional electronics manufacturing methods like components, chiplets, SOCs and the like, or if the functional elements should be made purely textile. But at the heart of it is this embroidered textile bus. And then we've also been able to demonstrate extremely high performance textile antennas for various applications. This is a small inductive power transfer antenna, just embroidered again on some fabric, some woven fabric. And this is a good example of just the flexibility that's provided to us by embroidery and why that has some value. So while this is not a therapy itself, there's some really interesting things you can do with antennas if you can build them in such a way that the user or the patient doesn't know that they're even in their garment, right? So I've shown you a few examples that are embroidery based. I did speak earlier to the fact that we can integrate these yarns directly in fabrics via other textile manufacturing methods, but Nautilus has converged on braiding and precision embroidery as the highest value integration technologies for building a broad range of systems, primarily focused around these multimodal sensor systems, right? So this is a little comparison chart. We could talk about this for a few days, but because our approach is really a textile first approach, we've constrained ourselves deliberately to using materials and methods that are compatible with textiles they follow the same design rules effectively that I outlined earlier in the talk that give textiles their unique properties. we don't have the same fundamental limitations that many competing approaches have. And because it is embroidery, we're not limited in the routing. We can over route, we can do two-dimensional routing, we can branch, we can cross yarns over each other. We have a huge amount of flexibility because that process is fundamentally additive. And the costs of it being additive associated with surface roughness and things like that are largely mitigated because by the scale of the materials that we're using, right? So those yarns are so small that they effectively, once embroidered, are embedded in the garment. They're not decorative embroidery. Electrically, because there isn't a cost or there isn't a significant system cost to integrating those yarns in the first place, we can leverage the surface area of the textile to integrate additional routes to provide better bus performance or reduce the, connect lines in parallel to reduce the linear resistance across the garment. And then from a survivability standpoint, those conductors, again, in the yarns are highly survivable. They are well protected, and the interconnect areas where we're actually connecting devices to those textiles are very small. So it's a relatively constrained problem about how to protect that area. And that provides us with a lot of flexibility, no pun intended, as to how we approach the basically the reinforcements and the encapsulation of those interconnects as a post process. So it's a pretty powerful enabling set of technologies for building all sorts of distributed multimodal sensing systems. And while our goal is to ultimately build these textile integrated systems for various applications, there's a lot that goes into building just systems, on their own. This is by no means an exhaustive list. This is some of the things that we do today, and there's more that isn't listed here. But those systems are designed to align to the constraints of the buses that we could make in textile. So we have developed some novel standards, serial peripheral interface for fabric integration, for example, things that we're still developing and intend to push out to the broader community when they're a bit more mature. And then we have Stitch is listed here. That's really our specialized textile integration toolchain, which is intended to basically bring together all the parts of not just what we're integrating, but the systems we want to build and how we want to build them. I'll speak to that in a bit. So if we want to maintain the value that's provided by these dynamic textile systems and maintain the value that's delivered by these microelectronic electrical components and subsystems, while integrating them, we have to consider what I've been speaking about up to this point, which is their technical effectiveness or their performance as part of an integrated system. But also, if we want to deliver that value at scale, manufacturability is a big problem. It's a big issue to address, and it's one that is non-trivial. Right, we've been working on this for about 10 years now, almost, and we've always constrained ourselves to developing materials and methods that align to fairly traditional, like known best practices in how you make textiles, and also how you integrate and build electronics. So that has forced us to be very deliberate about the choices we make. And now we're at a point where we have a fairly well understood, fairly robust set of processes that, again, are constrained at the moment by design to braiding, embroidery, and then we have several proprietary processes around interconnection, encapsulation, and everything that goes into basically finishing a system and making it, hardening it for use. And this image here is basically a black box that is a multi-process platform that we designed that's being manufactured for us. It's not to scale, weighs about 17,000 pounds. So a very precise system. But that is really the constraints we put on ourselves and the ways in which we've developed our methods such that they can be automated, coming off of an embroidery machine and going straight into an integration platform is really critical to how we can potentially just deliver these types of systems to world scale. And then Stitch, which I mentioned, is a tool chain that integrates our design tools and our manufacturing execution systems. So that's how you can not just scale up the production of one or two or three, novel, exquisite systems, but you could have a much higher mix, which accelerates testing, accelerates development, accelerates research, and really helps to reduce the cost of experimentation to the cost of running your machines, which is not trivial. And ultimately, the more shots you have on goal, the more likely you are to succeed with these things. So this is a very important part of Nautilus's roadmap for building impactful medical systems for sensing and therapies. So I'll stop there and open it up to questions.
Yeah, thank you, Jim. Yeah, for very interesting the talk on the smart textile. Can you hear me? Hello.
We can, yes.
Okay, cool. So now we are taking questions from the. Okay, yeah.
You're also working on a model system to design the electronic system. So I'm wondering what you said materials. So you have mentioned about a couple of materials, especially for fabrication. So have you experience about the high resistance materials?
Sean, I'm sorry, I can't hear whoever was just speaking. You need to get closer to the mic, I think.
Yeah, sorry about that. Can you hear us now?
I can hear you.
Okay, so.
So my question is that have you ever experienced about the high resistance materials for especially involved with your conductive threads?
High resistance materials?
Yes.
Sure. Yeah, absolutely. I mean, we build some, so the yarns are flexible in that we can integrate really any filamentous material. We want them to be of a small enough diameter that we're not compromising the flexibility of that yarn and the subsequent system in which they're integrated. But if it can be made in a filament, we can integrate it. So we've done everything from copper conductors through resistance heating wire, fiber optic, filaments, and kind of everything in between. So we build these in-house, we design them in-house, we have a library of materials, so we can really tune the parameters of the materials that we're integrating to meet the needs of the system.
Thank you, Jim. Yeah, and we have another question.
All right. So I understand that you are creating textiles for the applications of flexible electronics and stuff that conforms to the advantage of textiles. I was thinking along the lines of, since it's such a high precision method that you have here, can it possibly be used for the prototyping of rigid electronics as well, just high precision? Because a lot of the times when you're doing like the PCB design, a lot of the constraints is that like they will have to drill the holes in the board and stuff like that. And I'm thinking along the lines of maybe you can just, since it's an embroidered pattern, have a hole in it by nature, or something along those lines. What are your thoughts?
Yeah, that's a great question. I don't know if I said it, but that chiplet is the 12 pads on that chiplet are at 180 micron pitch. So that's the state of the art right now. And we are kind of always progressing, advancing the precision with which we can embroider these. So there are likely products and applications where we want to we could deliver value versus a traditional, like you said, a traditional rigid process. Where that line is not clear yet. Probably when it's something like a hybrid rigid flex application would be somewhere where that can make a lot of sense. But right now we're just continuing to progress, with some of the partners on the line here, actually, the precision with which we can do this embroidered integration.
Thank you for your response.
Thanks for your question.
Yes, thank you.
Yes, thank you, Jim. Yeah, I do
Sure.
have
Thank you.
a question. So for the smart textile, it has great advantages on the flexibility and also comfort. So how's the performance on the washability? Like what if, like as you see, the conductive stress or yarn exposed to the environment, and what if you have the water get onto the yarns? So how will it affect the system? Jim?
I'm sorry, Sean. I caught like every other word of what you said.
Okay, so in short, how do you, what's your taking on the smart textile on the washability? Like what if you have the system exposed to the water? So how does
Yeah,
affect the stability of the system?
sure. It's a hard problem. But we, fundamentally by trying to integrate devices that are as small as possible, we have to use a smaller volume of encapsulant than what you would traditionally use to waterproof a smart textile. So we don't have good data on this yet because it's not the processes aren't mature enough. We're going to be advancing that over the coming months and years, but fundamentally the smaller we can make the devices, the less encapsulant we need to use, and more or less it's the same problem as long as you are not compromising the flexibility of the textile, or really the intersection between the encapsulant and the device and the textile, which is non-trivial, but there's a broad range of materials and designs that could be suitable for that.
Thank you, Jim. Okay.
Thank you.
Okay. So now we go to our next speaker, Comfort Anderson. So you can share your screen with the audience.
Howdy, guys. Can you hear me?
Yes, clear and now. Yes.
All right, let me share a screen here, and then we should be able to dig right on in. So let's go right in, share.